Good day, I'm Dr. T, and let's talk about some batteries. Okay, when we talk about batteries, we're actually talking about multiple electric cells. So as a chemist, I generally want to jump in and talk about the electric cells. Because to make a battery, I just need to have more than one of those things. So let's talk about them, and they come in two predominant flavors. First, the galvanic cell, and this is usually what we think of when we think of a battery. Something that's generating electricity, something that's creating power. However, we can also have the alternative, an electrolytic cell. This is one that is using electricity, or using power, in order to move the electrons reverse from the direction they would prefer to go. These both have fairly significant uses. But let's first go to the galvanic cell. So I have a classic zinc-hydrogen reaction here. This is what you would get if you had a lemon battery. So I've got the anode and the cathode. The anode is going to be accepting electrons from the zinc half reaction. In fact, I have my chemical reaction separated and physically in two different containers. They don't have to be completely separated. I can use a semi-permeable membrane, and they do have to be connected in 2 points. First, through my electrodes. I have to be able to have the electrons run from one container to the other. Second, I need what's known as a salt bridge. This is a way for positive and negative charges to equilibrate out. If I keep dumping electrons over here, well, eventually this is going to get a negative charge. And after even a few electrons, that negative charge is going to stop the entire process. I have to be able to counteract that charge, allow ions, not electrons, but ions to flow back and forth between my two solutions. Because in both cases, there needs to be an electrolyte, something to allow my reaction to take place, and typically an aqueous phase. Now, I can use a salt bridge like I have here in this case. As the reaction goes, I'm going to start having chlorides flow in to the salt bridge and then kind of flow out that side. I can have, and it doesn't matter, I should say anions of some flavor, and then anions going in the reverse direction, or cations going in the opposite direction. This way, my charges cancel out. Alternatively, I can use a semi-permeable membrane. I can even kind of skip that step, but things tend to short circuit if you do. This is kind of in the details of getting a better electrical cell. That said, yay, we've got this. We've got an electrolyte, some way to move charge. I need to move charge from over here and here, shuffle that charges around, while the electrons take the long route through the wire, releasing energy that I can use in the form of electricity. Yay, a galvanic cell. Electrolytic cell, basically the same thing, just reversed. Instead of consuming power, or instead of giving power, it's going to consume it. So I'm going to connect this to a power source. And I'm just going to run everything in reverse. Now, of course, this particular reaction produces gas, so that's not going to be one that's particularly well reversible for obvious reasons. But, you know, if I had a supply of hydrogen gas here, it would be completely reversible. All I have to do is provide some power. Now, this has another interesting use for us. Sometimes we want to take ions in solution and stick them onto some metal. Electroplating is the classic case. Imagine you're watching TV and they've got that infomercial for those, you know, Luxembourg commemorative 24-karat gold-plated coins. You take some cheap metal and then you put a thin layer of gold on it. This is how you do it. So you take in here, inside by your cathode, that you're going to run some power through to it. You put some ions of whatever you want to stick on there. You run some electrons into it. The electrons then do a half reaction, which takes the ion of interest, say your gold or your whatever you would like to put on there, and then that does a reaction, forming the metal in the process. Now that metal just doesn't sink or doesn't float away, it sticks to the cathode. Yeah, I know I have it floating in the middle of nowhere, but it will stick to the cathode and it will coat it. And thus you can make a nice coating, which is useful for many applications, more so than just commemorative coins. Obviously over here, the galvanic cell, we've got a battery. We're all familiar with these guys, but we do have a couple of interesting other choices. One is known as a sacrificial electrode. We basically create a galvanic cell in a system where, hey, there could be problems. Now, here's a system that could have some problems. It's a hot water heater. Like what? Okay, so bear with me on this one. So hot water heaters, they are typically an iron tank. Now, they're also typically full of water because, you know, it's a hot water heater. Well, if you've got iron and you got water, you're going to get rust. The water allows a medium for the oxygen to react, get some nice iron oxide, and by nice I mean undesirable, and you got rust. So we're going to do two things to stop this. First, these are almost always going to be enamel coated. They're going to have a coating on them that is going to prevent this reaction from happening. Assuming there's no issues with your coating, and well, there's always issues. So hot water heaters are going to have a second feature, a backup line, what we call a sacrificial anode. So we're going to take a large magnesium rod. Magnesium is picked for a couple of reasons. For starters, this is in potentially your drinking water, and magnesium is actually something you need in your diet. So you're not going to get enough magnesium from this. Don't think you're going to get all your magnesium from your hot water heater, but it's not going to hurt you. Second, magnesium is what we call an active metal. Different metals have different preferences for electrons. The more active metals are more willing to give up their electrons. Now, some of them, like aluminum, form oxide coatings almost immediately, and therefore they give up a few electrons, then stop. But magnesium, well, it'll just keep going, and this reaction will keep going until I run out of magnesium. And here's the trick. It's giving up its electrons, not the iron. Magnesium is more active than the iron. So if the iron tries to corrode, tries to form Fe3+ instead of Fe, then it will get its electrons back, or it will get some electrons from the magnesium back. That way, oxidation still takes place. You can't get rid of that pesky oxygen. But what you're getting is magnesium oxide that, well, that sacrificial anode, it's just a metal bar. After a few years, turn off the water, drain the heater a little bit, pull the bar out, swap another one back in, and you're good to go. Your water heater will be lasting for a nice long time. We do the exact same thing with things like bridges, outboard motors, and anything where you've got iron, or steel, which is iron and a little bit of carbon, and water. And you don't want the rust. So a good old sacrificial anode. Yeah. Thank you, and have a wonderful day.